Our first summation formula that we are going to look at is what's called the arithmetic summation. It's the first thing we looked at, adding up the numbers from 1 to n. So this is 1 plus 2 plus 3 plus 4 until we get to n. There's a classic story around this that Newton or Gauss or whatever anyone's favorite mathematician is was asked in elementary school to add up the numbers from 1 to 100 or 1 to 1,000, or it changes based on the story. And this was given to him as just some busy work. The teacher really didn't want to teach. However, they were very clever and identified this formula and finished it within seconds as opposed to taking a full class period to do this. It's almost certainly not true. This is like a fable of mathematics that everybody tells each other. But it's a neat little story to explain why this formula is kind of nice. It allows you to add up lots of values very quickly. This formula I actually do use sometimes in my regular life. The other ones maybe not so much when you're at the grocery store. This one does show up sometimes though. So, little anecdote aside, how are we going to prove this? It's called a proposition. We're going to actually prove that this is correct. It says, for any n in the positive integers, this formula is true. That might tickle your sense and say, we're probably going to use induction here because we're proving something that's going to be true for every single integer. So we're going to prove this with induction. So proof. Because we weren't told directly to do induction here, I should probably tell the reader that we're going to use induction. So I'm going to write we prove this via mathematical induction. Mathematical induction. To prove stuff with induction, the first step is to always prove the base case. So our base case here, we're proving this for all n in the positive integers. The base case is n equals 1. For that, we have that the sum from I equals 1 to 1, that of I, what is that? That's us starting at 1 and going to 1, add up the value I. So this is just equal to 1. Furthermore, let's compare that to our desired quantity on the right, which is n times n plus 1 divided by 2. That's 1 times 2 divided by 2. That's 2. So it seems like the base case holds. We now must make our inductive assumption. So let's write that down. Inductive assumption. This is the thing we're going to assume is true. We're going to assume that the formula holds for n. Assume that P of n, where that means that the formula for n is true. I equals 1 to n of I is equal to n times n plus 1 divided by 2. Holds. I'm going to include that down on this line. We then want to show that P of n plus 1 is true, which is the formula for n plus 1. The sum from I equals 1 to n plus 1 of I is equal to the right-hand side of the formula plugging in n plus 1 is n plus 1 times n plus 2. So this is n plus 1 times quantity n plus 2 divided by 2. We want to show that that holds. Like we've seen with many inductive things in the past, we're going to start with one side of the thing we want to show and then manipulate it to try to use the inductive hypothesis somewhere along the way. So let us consider the summation from I equals 1 to n plus 1 of I. I can write this as n plus 1, which is the biggest term in the summation, plus the sum from I equals 1 to n of I. This says add up 1 to n, and then afterwards we add up n plus 1. This is in fact the same summation we had before. From our definition that we had in our very first video, this is actually exactly what the definition told us to do. You can peel off one term at a time in a summation recursively. That's what we're going to do here. This seems like it's a good idea, because now I have the sum from 1 to n of I, which is exactly verbatim what my inductive assumption knows stuff about. So I'm going to use my inductive assumption now, and say that this equals n plus 1 is going to remain as written, and I'm going to replace this summation with that fraction that our inductive hypothesis assumed was true. And because I use my inductive assumption, I want to comment somewhere that I use my inductive assumption. So off to the side here, I will justify this by saying by inductive assumption or hypothesis. Both are valid ways to write this. Inductive assumption. And now we have an algebra problem. I have some expression that I want to eventually show is equal to n plus 1 times n plus 2 divided by 2. So this is equal to, this is equal to. I'm going to factor out an n plus 1 out of both things, because I notice both terms have an n plus 1. So I have n plus 1 quantity times 1 plus n divided by 2. Alternatively, I could have tried to get a common denominator. Both approaches are equally valid. I now am going to get a common denominator between those two fractions, and I get that this is equal to quantity m plus 1 times quantity 2 plus n divided by 2. This is written in a funny form, but this is my final goal. I'm going to rewrite it just to make sure it looks identical to the thing I wanted to prove. This is equal to n plus 1 times n plus 2 divided by 2, which was our end goal. So, p of n plus 1 is true, because we started with the left-hand side of the thing we wanted to show, and did algebra and used our inductive hypothesis to eventually show that the right-hand side was equivalent to it. So, if p of n plus 1 is true, the result follows by mathematical induction. Therefore, or thus, the result follows by the principle of mathematical induction. Principle of mathematical induction. And that's the end of our proof. One of the primary reasons that we learned induction for the purposes of this class was to be able to prove things like this. We're going to be using summations so much going forward that we really want to have formulas when we see these well-known summations. This is called an arithmetic summation. Will show up lots of times in this class and is a very useful formula, sometimes even in your regular everyday life when you're just trying to add things up.